So can start soon.
Hello and good morning, everyone. So we'll start off with the classes. Prajwal.
Yes. Tell me, sir. Yes.
Yes. Prajwal.
Yes.
Are you the co-host or am I the co-host? What is this?
You are the co-host.
I'm the co-host. Okay, fine.
Okay.
You will be allowing all the students, no, now?
Do we do recording in our cloud or there?
I think if you can record it in your system. It's always better, no?
Okay.
Record it in your system. And YouTube is our channel, no?
Yes, yes.
Okay, fine. So no issues there. Wonderful. So I think we'll start with the discussion. Students, I hope I am audible to all of you. I am allowing all of you to unmute wherever you need. You can answer me by unmuting, no issue at all. But as I keep telling you, you need to actually use it very, very judiciously. Okay. Whenever you want to ask a question, you can switch on the mic. Otherwise, keep the mic in the mute mode. Today, we'll be discussing about capacitors. Very important as far as your, say, KCET is concerned or DSAT is concerned. This will be a very important chapter. Okay, you can always see that 2 to 3 questions come from this chapter. Along with that, very similar to this particular capacitor will be resistors. So you can treat both of them sort of somewhat similar ideas, and then one can give a clue to the other one. And in both the aspects, I would say capacitors is going to be an important chapter for your competitive examination. I would say in the case of mains and NEET, if someone is interested in, okay, you will find that there will be important types of questions coming from this idea, especially the dielectric, okay, the dielectric medium, energy stored in the capacitor. All that will be very important for your mains and the NEET examination. So as usual, what we'll do first is look at the important ideas, concepts, and then start solving problems. So the capacitor essentially comes with some amount of capacitance. Capacitance by definition is the ability of a conductor to store charges. Now, how do we define capacitance? Is Q by V. What is the unit for capacitance? Unit for capacitance is farads.
Alright.
And 1 farad is same as 1 coulomb per volt. 1 coulomb per volt. So this is the unit that we are going to basically use for measuring the capacitance. Now, capacitance of a conductor of a spherical conductor, let me be very careful, of a spherical conductor of radius r is given by of radius r is given by 4 pi epsilon naught r, where r is the radius of this and epsilon naught is the permittivity of free space. It has a value of 8.854 into 10 to the power minus 12 SI units. It's basically Newton meter square, Coulomb square by Newton meter square. Okay, so that's the unit for the epsilon naught. Now, if you keep it in a dielectric medium, then the capacitance will be given as 4 pi epsilon naught epsilon r into r, where epsilon r is called the relative permittivity, or another word for it is dielectric constant. Epsilon r value is given to be k. Many times we write this as k also. So C will be equal to 4 pi epsilon naught k r. Few important things to note. Each one can be a good question. So whenever I give you a note, that's the intention of it. First one is C is independent of charge and potential. It doesn't depend on it. Okay, it's independent of that. So it only depends on C only depends on the dimensions of the conductor. Okay, that's R in this case. Then it depends on the dielectric constant of the medium surrounding it. So call it as K. So these are the two dependencies that you will have for the capacitance. And it doesn't really depend on other things. Okay. Now for the next idea, if you all have done it, I'll go to my next page. Can I go to the next page?
Yes, sir.
Okay. Now we will look at different types of capacitors. Now, capacitor is a device which has two similar conductors kept close to each other. one conductor is charged. One conductor is charged. The other conductor is connected to ground. That arrangement, in fact, is called capacitor. So if I have one plate here like this, I'm going to add some charge onto it. The other plate is simply kept by the closed by, and then there will be an induction here minus Q, and this is connected to ground. Now, because of this arrangement, there will be a potential difference, which I call it as delta V. And if the charge given to this is Q, then the capacitance will be written as Q by delta V. So this is what a capacitor is given to be. In the case of conductor, it was simply Q by V. Here it is Q by delta V. Remember that. Okay. Difference in the potential, which we call it as voltage. I think hereafter I will start calling this as the voltage or the potential difference. I'll be using that word hereafter. Now, the three different kinds of capacitors that you have is, number one is the parallel plate capacitor. So if you have a capacitor here like this, now this will basically have an area A. The cross-section area of the two plates are given to be A, and the separation between them is given to be D. Then you can show that the capacitance is given to be A epsilon naught by D. So this is the expression for the capacitance of the capacitor. Okay, of a parallel plate capacitor. Note. Number one, A is the area of the plate. Now this can be a rectangular plate. In that case, area will be equal to AB. It can be like a disk. In that case, area will be equal to pi r square. Now generally, the separation between the plates D is very small when compared to the dimensions of the plate. So length and breadth or radius will be very large when compared to this separation. So that is always an understanding that you need to have. And then also you'll find that if you place a dielectric between the two plates, then the capacitance will be equal to A epsilon naught K by D. Now, if air is between the plates, air also is a good dielectric medium, then the capacitor is called as the air capacitor. So this will be equal to simply A epsilon naught by D. With the dielectric, C will be equal to A epsilon naught K by D. So I'll call this as C air, this as C dielectric. Now, if you take the ratio of CD to C air, you always get K. This is a very important idea. Lot of problems basically will be on this itself. They give you the capacitance in the dielectric with the dielectric medium and with the air, and you are asked to find out what the dielectric constant is. So K should be given by CD by CA. So this is an important idea. So keep this in mind for the parallel plate capacitor. Now, if you all have written down this, I would like to go to my next page for the next type of capacitor. Can I?
Yes, sir.
Okay. Now, the second type of capacitor, I'll call this as the spherical capacitor. Now, there are two varieties of spherical capacitors available. First one is a capacitor basically which has two concentric shells, one of radius A, the other one of radius B, and I give a charge Q onto the inner shell. Let us say the charge given to this is Q, and the outer shell is connected to ground. Okay, this is one type. So there will be a negative charge induced on this here on the outer shell, and this is connected to the ground. Now the capacitance here of this is given by 4 pi epsilon naught AB by B minus A. Okay, this is the capacitance for this arrangement. You also have another kind of spherical capacitor, which will be the inner one is grounded, and the outer one actually is given a charge Q. While discussing the electric potential, I think I had mentioned about the potential difference because of this. If the charge on this is Q, there will be a charge here which will be equal to QA by B. So the charge on this will be negative and is given by minus QA by B. Now, in this case, the expression for the capacitance is 4 pi epsilon naught B square by B minus A Now, if I call this as C1 and this as C2, you will find that for a given radius, C2 will always be greater than C1. So the better arrangement for the capacitance is always the second case. Okay, not the first case, but rather the second case will be a better arrangement. If you all have written down this, I'll go to my next case, which will be the cylindrical capacitor. Okay, are you all done with this? Can I go to the next page?
Yes, sir.
Okay, so you want me to write a little darker. Okay, I'll do that. I'll remember to do that hereafter. The next type is the cylindrical capacitor. In this case, the capacitor will basically have two cylinders, okay, like this. They both are kept coaxially. We all understand by the meaning of being coaxial. In this way, the inner cylinder is given a charge Q. The result of which there will be a minus charge induced on the inner surface of the outer cylinder. And if the radius of this is given to be inner cylinder has a radius A, outer cylinder has a radius B, and also the outer cylinder is connected to ground. Now these cylinders are supposed to have a very, very large length. Okay, L will be greater than A or B. Okay, in such a case, you can show that capacitance will be equal to 2 pi epsilon naught L divided by ln B by A. Ln B by A is the expression for the cylindrical capacitor. This also will be an important idea. You will actually see this at a little higher level. NCERT book doesn't give you this, but this sometimes they ask you still in the mains examination. So better be careful about it. Okay. Now, having done with different capacitors, let us now look at how to charge a capacitor. How to charge a capacitor. Now, the simplest circuit for charging a capacitor is the following. You have a capacitor, you connect it to a cell of EMF E, and internal resistance R. Now, this will basically charge the capacitor, and then the capacitors will basically acquire a charge which is equal to Q. And there will be a voltage here V. So we say that the charging will happen until voltage across the capacitor will become equal to EMF of the cell. So the charge therefore on the capacitor will be equal to simply C into E, where C is the capacitance of this. So C into E, where because V is same as E, so you get this to be equal to this. So this is a very important relation. The second one is charging of a capacitor will lead to energy storage. Energy storage in the capacitor. Energy storage in the capacitor. Okay. The energy stored in the capacitor is given to be half CV square. Can also be written as half Q square by C. So this is the energy stored in a capacitor is given to be. Okay. Then at this point in time, I also want to mention one more important idea. Work done by the battery or the cell in charging a capacitor is given to be CV square. That implies that there is some loss of energy because work done by the battery is CV square. Energy stored is only half CV square. So there's a loss of energy while charging, and that's equal to half CV square. So loss of energy during charging is given to be half CV square. So these 3 points are quite important for you to understand. This is what happens during charging of a capacitor. Okay. If you all are okay with this, I'll go to my next page and to the next idea. Can I go to the next page?
Yes, sir.
I hope you all are writing down these points. Very important. Okay, don't wait for my notes. You can write it down yourself. When I give you the notes, you can actually cross-check and see whether you're left out. Once you write, then it registers in your mind very well, and therefore writing is important for me. See, the next idea that I have here is about the combination of capacitors. In this, we have the series combination, which will basically give rise to the capacitors being connected one by the side of the other in this way, and then connected to a battery of EMF E. Now each one has different capacitance, and the voltage drops will also be different. But what will be the same is the charge on all of them. So whenever you have a series combination, points to be remembered as charge on all capacitors are same. Voltage drop on each of them will be different. Okay, will be different. Okay, the potential drop or the voltage will be different across the capacitors. Now the next question that we get is, what will be the equivalent capacitance? Equivalent capacitance in the case of series combination is 1 by C1 plus 1 by C2 plus 1 by C3. This is how they combine. This is how they combine. Okay. Now, the charge Q on the each capacitor, because this also can be a question, they keep asking you this question, will be equal to whatever is the EMF of the cell into the effective capacitance. The charge on the capacitors, Q will be equal to, each one will have this E into CS, E into CS.
ನಿಮ್ ಕಾಲೇಜ್ ನೋಡ್ ಕಳ್ಸಿದ್ದು ಅವನು ಮಾಡ್ತಾ ಇಂಟರ್ನ್ಶಿಪ್ ಮನ್ಯಾಗ ಬರ್ತಾವಂತ ರೊಕ್ಕ
E into C1, E into CS rather. Okay. Now the other question generally asked is, what is the voltage drop across each capacitor? All the formulas, in fact, I'm giving you here. This will be equal to E into C2 plus C3 divided by C1 plus C2 plus C3. All right. So this is how one can write down the expression for the capacitance here like this. Right. Similarly for V2 and V3 and so on and so forth. You can easily show that V1 plus V2 plus V3 will be equal to E. This again comes because of energy conservation or Kirchhoff's laws. Kirchhoff's law. Okay. So the important points in the series combination I'm trying to give here. Now, if you have n identical capacitors connected in series, then you can show that C will be equal to, CS will be equal to C divided by N. Okay, C divided by N. And also, another point, in fact, I would like to make here, which is going to be very helpful for your problem solving, is this. If I have only two capacitors in series, then CS can be written as C1 C2 by C1 plus C2. Okay, this is how we can write down the capacitance as. Now, similarly, if the voltage here is V1 and the voltage here is V2, then you can show that V1 will be equal to E into C2 divided by C1 plus C2. V2 will be given as E into C1 divided by C1 plus C2. Do you all see the difference? V1, C2 here, V2, C1 here. Okay, so whenever you want to calculate voltage across the first capacitor, it is the EMF into C2, the other capacitor, divided by this. You can further show that in case of series combination, V1 by V2 will be equal to C2 by C1. There's an inverse relation between the voltage and the capacitance. Okay, that's an important point to note here in this case. So if you all are okay with this, I would like to now go to my next page and look at the parallel combination. Have you all written down this? So the next one will be the parallel combination. Okay, and in the, one second. In the parallel combination, I will basically have the capacitors connected across the same terminal of the battery. All these things you know very well. I'm only trying to actually give you a recap of this, and you all should write it down in one place, because just before the examination, you will find this to be a very, very handy one. C1, C2, C3. Now, if the EMF is E, then you'll find that the amount of charge on each capacitor will now be different. Q1, Q2, Q3. It can be shown that the total charge here will be equal to Q1 plus Q2 plus Q3. So it will actually have more ability to store charge, okay, which will be Q1 plus Q2 plus Q3. All of them can store more and more charge. Now, the voltage across them will be same. So you'll find that V1 will be equal to V2, will be equal to V3, equal to EMF of the cell. EMF of the cell. This is my first point here. The second point that I want to make here is what will be the effective or the equivalent capacitance. The equivalent capacitance will be equal to C1 plus C2. C1 plus C2. Now the obvious question that we'll always have is what will be the charge on each capacitor. Q1 will be equal to C1 into E. Q2 will be equal to C2 into E. So the charge on the capacitors are going to be different. And this is how one can write down the charge on each capacitor to be given us. The total charge Q can be written as E into Cp, where Cp is the effective capacitance of the combination. So this is something which you all should very well know about. Okay. Fine. I think with the parallel combination, this is what I have. I'll go to my next page and look at the other aspects of capacitors now. Series and parallel we have looked at. Now we will look at the some more aspects of it, especially what I call it as the pre-charged capacitors. You'll have plenty of problems on the idea of the pre-charged capacitors. So let us say that I take a capacitor, charge it to a voltage V1, and it is C. So there's a plus charge here and there's a minus charge here. I take another capacitor like this of capacitance C2 and charge it to a voltage V2. Now the voltage is different, okay? It has been charged to a different voltage. Now what we'll do is we will connect them in parallel. That is, take the positive plate of both of them, connect it together. So positive plates are connected together, negative plates are connected together. Then we all know that these two capacitors will attain a common voltage. The common voltage is given to be C1 V1 plus C2 V2 divided by C1 plus C2. This in fact is called as the common voltage attained by the capacitor. Now, some amount of charge will flow from one capacitor to another capacitor. It will flow until both of them will have the same voltage. Okay. Now the transfer of charge Q can be written as C1 V1 minus C1 into V, where V is the common voltage. So this was the earlier charge. Now after, actually it loses the charge, in fact, is basically after the combination is this, connection is this. So therefore the loss of charge or the transfer of the charge is always given by this one. So C1 into V1 minus V is the amount of charge that gets transferred. Yes, Shivanik, any problem? Now due to this, due to the transfer of charge, there will be a loss of energy, and this loss of energy will be written as the initial energy minus the final energy, which will be half C1 V1 square plus half C2 V2 square minus half C1 plus C2 into V square. So this will be the loss of energy when the capacitors are connected in this way. Pre-charged capacitors are connected in this way. This is a very important idea. I think you all should make a clear note of this. Lot of problems are asked on this idea itself. Okay, this loss of energy will come out as heat generation. So another way of asking this question is, what is the amount of heat generated when two pre-charged capacitors are connected in parallel like this? So that can be an interesting question. Okay, if you all are done with this, can I now go to my next idea? I would like to do with with dielectric, what will happen? So I'll go to my next idea. Hope you all have written down this. The next idea is capacitors with dielectric medium. Now, if you basically have a parallel plate capacitor, this problem is generally done for the parallel plate capacitors. I think if you don't switch off the mics, I will not allow you to unmute yourself at all. I told you, be responsible. Okay, remember you are in a classroom and you can't disturb everyone. There are other 75, 76 students there. You can't disturb them. So make sure that the mic is actually kept off. So this actually has an area A, this actually has an area A, and the separation is given to be D. Now I can fill up this region here with a dielectric medium. Okay, the entire area I can fill it up with a dielectric medium like this. So this medium here of constant K will immediately increase the capacitance to A epsilon naught K by D. All right. Now this kind of capacitance, I'm going to represent it like this. So this is your constant dielectric medium, and these are the plates. So I can now think of many combinations for this case. The first combination is where I have the dielectric medium made up of two different constants. Of constant K1, K2, D1, D2. All right. Now this actually has an area A. Now this is equivalent to having two capacitors connected in series with a constant K1 and separation D1. This is K2 and D2. And hence I will have the expression for the effective capacitance to be equal to 1 by C1 plus 1 by C2. Or in other words, I'll have the expression for the capacitance as A epsilon naught by D1 by K1 plus D2 by K2. D2 by K2. D2 by K2. This is a very important kind of problem. You again have a lot of problems coming here like this. Few interesting point to note. Note number one. If one of the medium is a conductor, then for conductor, the dielectric constant is given to be infinity, and therefore in such a case, the capacitance will be equal to A epsilon naught by D1 by K1, or will be equal to A epsilon naught K1 by D1 by D1. And therefore, for the case of a capacitor with one of the medium as a conductor, so here I have one of the medium here given to be a conductor here. K2 to be equal to infinity means a conductor. Then effectively the capacitor is only between this one, so which actually has a width of D1, and hence this becomes A epsilon K by D1. Okay, so that's an important point to note here for this. If you all have written down this, I want to go to my next page and look at the next case. Mr. Sinu, switch off your video. The second case is when I have the dielectric between the two plates filled up in this manner. K1, K2, A1, A2. So here, this will be like a parallel combination. So this will be equivalent to having two capacitors which are connected parallelly to each other. This has K1, A1. This has K2, A2. Now the capacitance of this would be simply C1 plus C2. In other words, Cp will be equal to A1 K1 plus A2 K2 epsilon naught by D, because the separation between them is given to be D anyway. And therefore, you have the capacitance of this combination given in this way. Okay, so this will be a very interesting case, as you can find out. Okay. Now we'll come to the last kind of problems here, last type of ones. Okay, I will look at some special circuits. Some special circuits in the capacitors. Okay. Now, some of the special circuit that I want to consider is number one, the Wheatstone network. The Wheatstone network. Now, you all have seen Wheatstone network in the case of resistor. It can also be there for capacitors. So I have a capacitors here connected like this. And then in this way here, this way here. So this in fact is called as a V-stone network. Here I have C1, C2, C3, C4, and C0. And C0. Right. So if C1 by C2 is equal to C3 by C4, then it's called in fact as a balanced network. Now, whenever you have a balanced network, charge on C0 will be 0. There's no charge on this capacitor. And that would imply that I can basically write down this circuit simply as this. C1 and C2 will be in series. In turn, C3 and C4 will be in series, and they are all in parallel. So the circuit, I can remove that C0. So you can remove this C0, and hence you get a capacitance like this. So now finding the effective capacitance across AB is quite simple. So this is one of the important types of circuits that we'll be looking at. Note again here 1. The same circuit, whatever I showed you here, can also be represented in this manner. Okay, can also be represented in this manner. This is another way of writing down the capacitor. C1, okay, C2, C3. No, I think this is C2. Take this as C3 and this as C4. Or maybe I'll just rewrite this two capacitors. This would be an easier way of doing it. C1 and C3. This should be C0. So this is connected to a battery. A battery here of EMF E. So same way, this is also the same circuit. Okay, same thing that has been represented here. This also is the other form of V-stone network. So if they show you a network like this, immediately identify that to be a V-stone network. Okay, so I think with this note, let me go to my next important type of problem. Okay, which is again another network. Can I do that? Can I go to my next network? What do you say, all of you?
Yes, sir.
The second type of network that I would like to take you through is what is called as the symmetric circuits. Okay. Now, I'm going to look at what is called as symmetric circuits, which will be very difficult if you look at it. Okay, but when you start, say, simplifying it, you will find that it can be done very easily, but requires a little trick. So I'm trying to actually explain you what that is going to be here. Let us say that I have a combination of capacitors given like this. And you have to find out what is the effective capacitance across A, B. Okay, you have to find out what CAB is. So if you want to do that, the simple, all of them are C, by the way, all of them are C. This is called as a symmetric circuit because you will find that if you either enter from A or enter from B, the network looks exactly the same. There's no difference at all. Now, in a circuit like this, what you can always assume is if there's some amount of charge coming in here, that will get redistributed as Q1, Q2, and Q3. All of them will again combine to give you back a charge Q. So this charge here will be Q1, this will be Q2, and this will be Q3. Now, since the same amount of charge is there here, Q2, the same amount of charge will go to this capacitor. Hence, there is no connection here. You can remove this connection. In other words, these two capacitors can be actually removed. Now, if you do that, then the circuit simplifies so easily. So the circuit, in fact, will just turn out to be this. Will turn out to be this. Because I can remove that middle one, and now it is so simple. C and C in series, this becomes C by 2. This will be C by 2, C by 2. Now, so therefore, you will have 3 capacitors now connected in parallel of the value C by 2. So therefore, the effective capacitance will be 3C by 2, and that can be done so easily, isn't it? So this is what happens in the case of combination of capacitors. Similarly, you can have other circuits as well. So let me now give you a very interesting set of capacitors. All right, and okay, C naught can be a capacitor or a galvanometer. Generally, in the case of capacitor network, they don't use galvanometer. Galvanometer is used in case of the resistance networks. For capacitor, somehow, because there's no flow of current, isn't it? So galvanometer has actually very little application there. Hence, no one uses galvanometer. That was a question asked in the chat, so I thought I should answer that. Okay, so next type of capacitor, the network here would be combination of 12 capacitors which are taken and then formed a cube. Okay, I'm going to make a cube out of this capacitor like this. So there are 12 of them. We are going to connect all of them here and then figure out how to do that. Okay, so let's say that so I'm going to place actually a capacitor at all the terminals here like this. Everywhere there is one capacitor connected at the edges. So each edge basically will have a capacitor connected here. And let all of them be equal to C each. Now I'll call this end A, this point as B, the diagonally opposite as B, this point as C, and maybe I should avoid C, isn't it? Because C is capacitance here. So let me avoid writing this as C, but rather take this as D and this as E. Now the effective capacitance across AB will be given as across AB will be given as 6 by 5 C. 6 by 5 C effective across AB. In the same way, effective capacitors across AD, across these two, will be given as 4 by 3 C. 4 by 3 C. Lastly, I will have the capacitance, which is given to be across A and E. CAE across AE will be given by 12 by 7 C. Is given as 12 by 7 C. So this is in fact the effective capacitance of a circuit like this. All right. Last type of special circuit that I want to consider is not a symmetric circuit, but rather this will be what is called as an infinite ladder. See, there are some students who would also be preparing for the mains examination and the NEET examination. For them, this is going to be an important one. And of late, I have found that this KCET also has increased its level of, say, questions. So this can always be a type of question that can come across. Please remember, it is very difficult to predict the questions for the CET examination. It is not like the board examination, where you can say, this is the type of question which comes. If someone is telling you that you take, this is the question that you're going to get in KCET, please don't believe them. You can't predict questions in CET. CET can be different, sometimes very easy, sometimes very difficult, and therefore you need to prepare for the concepts very well. So look at all these concepts and then try to look at them carefully. So let us say that I have a capacitor here given to be 1 microfarad and 2 microfarad. Then I'll have again 1 microfarad and 2 microfarad connected here like this. So first step is 1 and 2 microfarad. Second step is again 1 and 2 microfarad connected to this. Third one also will be a similar combination, 1 microfarad and 2 microfarad. And this connection goes on in this way. Will go on up to infinity. So now here you will have A and B. This is called as an infinite adder because the steps will go on actually adding up like this. Now the question generally is to find what is the effective capacitance across AB. Now the method is something that I want to tell you all about. See, what I'll do is I will rewrite this circuit as this way. This point is there, no? C, I call it as C and D. So I'm going to say that the CD entire thing up to infinity will be replaced with one single capacitor, which will be equal to C CD. Okay, this will be the capacitor. But what I will say is, because I've just removed one from an infinite network, the effective capacitor across AB should be same as the effective capacitor across CD as well. CD as well. And therefore I can say that I'll be getting this as instead of CCD, I'll write as CAB. So the equivalent capacitance will be therefore CAB will be equal to 1 into the combination of these two will give me CAB plus 2 divided by CAB plus 3. 2 plus 1, 3 you get 3. You get 3. So I get an equation here for CAB now. This will be CAB square plus 3CAB is equal to CAB plus 2. So in other words, we get this to be CAB square plus 2CAB minus 2 is equal to 0. So this is a quadratic equation. So solve this quadratic equation to get CAB. So in that case, CAB will be equal to minus 2 plus or minus root of 4, and then this will become plus 8, isn't it? Plus 8 divided by 2. So the answer to this question therefore is CAB will be equal to minus 2. Only take plus, don't take the minus, will be root 12. Root 12 can be written as, what can root 12 be written as? 2 root 3, right? 2 root 3 divided by 2. Hence, CAB will be equal to root 3 minus 1 microfarads. So I can get the answer for CAB in this way. Okay, so with this, whatever I wanted to discuss in capacitors, I have done it. So I think it is time for us to start solving the problems. If you all are ready, I would like to start solving problems now, the MCQs. Can we start?
Yes, sir.
Okay, good. So let's look at one by one now. I'll be also sharing this one with you. Just give me a minute's time. Keep going through the first problem. Okay. Problem number 1. Two capacitors of 2 microfarad, 5 micro connected to two batteries as shown in the figure. then the potential difference in volts between the plates A, B is. Okay, this is a nice question. It's a nice question. One way of actually working out this problem is to rewrite this circuit in a little different way. Look at it. A and B basically are like series combination of capacitors connected in this way. 18 volts plus here, terminal is connected to the plus of 11. So now you can basically therefore write this as, these two are also in series, mind you. Okay, these two are also in series. So can be written as 18 volts like this. Okay, this will be 18 volts, this will be 11 volts. So you can rewrite the expression, rewrite the circuit in this way. Both of them will have the same charge. Now it is so simple to actually obtain. What is the net EMF of this? This will be an improper connection. This will be an improper connection of crystal. If it is an improper connection, then you can say that this circuit will now be simplified in the following way. I can replace this one, the two of the cells with just one, and that will be equal to 7 volts. That will be equal to, sorry, how much is that? Yeah, 7 volts, isn't it? 7 volts. 18 minus 11 will be 7. Who is that Corona, I say? Why don't you actually mute? Why do you want to trouble everyone? True to your name, huh? Now, what is that you want? You want to know what is the potential difference across plate A, that is across 2 microfarad capacitor. You have to find out what V is. If you recollect the formula, I had told you that V1 is equal to E times C2 by C1 plus C2. So E is equal to 7. C2 here is going to be 5 divided by 5 plus 2. So therefore, the answer to this question should be 5 volts. So the circuit is given in a little different way, that's all. Okay, but has to be understood to be like a series combination. So therefore, I would consider this to be a very important problem where you have to understand that this essentially is a series combination. It appears like a parallel combination, but actually it is not. It is like a series combination where I took all the capacitors on one side and the batteries on the other side. So I could get the answer quite easily here. And now for the second question. 5 capacitors of 10 microfarad capacitor each are connected to a DC potential of 100 volts as shown in the figure. The equivalent capacitance between A and B is. So look at it. This appears to be a balanced Wheatstone network, and therefore I can remove this C0, which is 10 microfarad again. So what will be the equivalent of this? Yes, many of you are giving me the answers already. Wonderful. Option 4 is the correct one. Yes, true. You're right. So 10 and 10 in series, in turn parallel with 10 and 10 in series. So 10, 10, 10 and 10. So effectively, this will be now a series combination. So 5 microfarads, 5 microfarads. So together parallel combination will give you 10 microfarads, and therefore that's the correct one. Perfect. Quite a good one. Okay. Wonderful. Next question also is very interesting. Okay, here, third question, I need to tell you something here. Under what is called a steady state, that is when the capacitor gets completely charged, then current in the circuit is 0 and all the voltage will be across the capacitor. No other element in fact will have any voltage. All of them will be only across the capacitor. So now look at the circuit. Consider the circuit in the figure. Find the charge on the capacitor C between A and D. So between this and this, I have to find out the charge on the capacitor, this part, not this one or this one. Now we can say that this whole thing is one circuit. The other one is this circuit. So the entire voltage will be across this capacitor. So the voltage across this whole thing here will be equal to 0. When there is no potential anywhere in this region, how can you expect any charge on the capacitor? The charge on the capacitor also will be 0. Okay, I hope you all got this idea. This is called steady state of the capacitor. That is when it is completely charged. This is what happens. Okay, very nice. So all of you are in agreement with my answer for the third question. That's what they are saying in the chat. So maybe I'll go to my next set of questions. All right. Explain first question. Okay. Now, first question, I took the two capacitors in series, two cells also in series. Now, the reason why I connected this positive 18 volts and 11 volts in this way is because the positive is connected to the positive and negative is connected in this way. And therefore, the combination should be like this, isn't it? Negative, negative, positive, positive, okay, through the capacitors. So that is why I can write down the circuit like this. Now, if there is 18 volts here, 11 volts in the opposite direction, what is the net EMF? Net EMF will be now E1 minus E2. So 18 minus 11 is 7 volts. Now, this is like two capacitors connected across 7 volts per cell. Hence, the voltage across the 2 microfarad, that's what they're asking you, plates across this A, will be given by EC2 by C1 plus C2. Go to my discussion on the series combination. There you will find this expression. So this will be 7 into 5 divided by 5 plus 2. So that will turn out to be 5 volts. Is that it? Did you understand that? Someone asked me for this. So, okay, good. Let's go to the next set of questions. Fourth one. 4 microfarad capacitor and resistance 2.5 mega ohm are in series with 12 volts battery. Find the time after which the potential difference across the capacitor is 3 times the potential difference across the resistor. Okay. Fourth question, I would like to simply leave this out. Only if the time permits, I will do it in the end. This basically corresponds to what is called as the transient circuit. The best way would be to do after resistor, but even if you leave out, shouldn't be a big issue. So I'm not going to really worry about fourth one. Only if time permits, I'll do it in the end. I don't want to waste much of my time on that question right now. Two metallic sphere of radius 1 centimeter and 2 centimeter are given a charge of so much respectively. If they're connected by a conducting wire, the final charge on the smaller sphere is to be obtained. All right. So to find out what is the charge on the smaller sphere. Now, the easiest way to do this problem is the following. Find out first what is the total charge of the system given to be. For one, they're giving a charge of 10 to the power minus 2. Other one is 5 into 10 to the power minus 2. So this will be together 6 into 10 to the power minus 2 charge. Coulomb, sorry. This is the total charge here. Now, you have two spheres, one of radius 1 centimeter, the other one of radius 2 centimeters. They're connected by a wire. So the moment you connect by a wire, potential of both of them will be same. And therefore, you can show that if the charge here is Q1, if the charge here is Q2, then you can show that Q1 by 4 pi epsilon naught B will be, sorry, A, I'm so sorry, by A will be equal to Q2 by 4 pi epsilon naught into B. Or in other words, you can show that Q1 by Q2 will be equal to A by B. So what is Q1 by Q2 equal to? Q1 by Q2 is equal to A by B, isn't it? So A by B is 1 by 2. And therefore you can show that Q2 will be equal to 2 times Q1. And further, you have Q1 plus Q2 is equal to 6 into 10 to the power minus 2 coulomb. Now, from these two equations, you can immediately get what Q1 is. Very simple, isn't it? Q1 should be equal to 2 into 10 to the power minus 2 coulomb. Just think about it. Because you have Q2 by Q1 is equal to 2. Q1 plus Q2 is equal to 6. So when will that happen? When Q1 is equal to 2 and Q2 is equal to 4 into 10 to the power minus 2 coulomb. So therefore, the answer to this question should be pretty simple. It should be equal to Q into 10 to the power minus 2. It is for a smaller sphere, isn't it? So the fifth one, the answer is fourth option. Is that clear? Is that okay with all of you? Can I go to my next problem, which seems to be quite interesting? In the given circuit, the charge on the 4 microfarad capacitor will be, I have to find out what will be the charge on this part. Now, if you want to find out the charge on this part, the quickest way of doing this problem is consider only this part of the circuit. Don't even worry about 3 microfarad capacitor. Only consider this. Now, this 4 microfarad capacitor in turn parallel with 1 and 5 here, I can say that the voltage drop across this will be equal to 10 volts. Will be equal to 10 volts, right? This is what, in fact, the circuit is. Only this part, if you consider, the voltage drop on this is 10 volts. Okay. Now, you have to find out what is the charge on this part, isn't it? Now, to find out the charge on the 4 microfarad capacitor, find the voltage across 4 microfarad capacitor. And that is very simple to do. V1 is equal to E into C2 divided by C1 plus C2. In this case, C2 will be a combination of these two. 5 and 1 together will be 6 microfarad. So C2 will be 6 microfarad. C1 is 4 microfarad. And E in this case is given to be 10 volts. So substitute all that and do it. So 10 into 6 divided by 10. C1 plus C2, 6 plus 4 is 10. So 10 cancel off, and you have this to be equal to 6 volts. Now, if you know the voltage across the 4 microfarad capacitor, then the charge, yes, many of you are giving the answer. I'm so happy about it. Charge Q will be equal to V1 into C4. So V1 is 6 into 4 is 24 microcoulomb is the answer to this question. So where is the answer for this second one? In fact, is the right option. Many of you are giving me in the chat that option 2 is the right one. Correct. Okay, very nice. I'm so happy. There are some 6-7 students who have already done this and then given me the answer. Fantastic, I say. Fantastic. So let's go to the next set of questions. Okay. 4 capacitors are connected in the circuit shown in the figure. The effective capacitance between A and B is, so this point and this point I have to find out what is the capacitance. Look at the student. It's very interesting. If this point is A, this point also is A, right? And therefore the circuit is like this. You have one capacitor here connected and another connected here, these two. So 2 and 12. Between this and this, I have, this is your A, this point is your B. All right, this point is your B. Now between this point, maybe call it as a D, and A, I have one capacitor. So connect that 2 microfarad capacitor here between A and D, no issues. Now between B and A, you have one more capacitor. So you need to connect one more capacitor here like this for the combination. So this will be your 2 microfarad capacitor. So very interesting circuit. So you have 2 and 2 in parallel. So I know what to do with them. So 2 and 2 in parallel will be 4 microfarad capacitor. Then so let's rewrite this as 1 4 microfarad capacitor in series with a 12 microfarad capacitor. Then connect back the other one. So 2. You need to really keep an eye on that as well. So this is your A and this is your B. Now these two are in series connection. Now for a series connection, you should be very quick in solving this. Series combination will always be C1, C2 by C1 plus C2. So 12 into 4 divided by 12 plus 4. So 12 plus 4 will be 16. So 12 into 4 divided by 16, 4 ones are, 4 fours are, 4 ones are, 4 threes are. So this basically will become 3 microfarad capacitors connected with a 2 microfarad capacitor to give you point A and B. Fantastic, isn't it? So CAB will be equal to 3 plus 2 is 5 microfarad capacitor. So the answer to this question should be 5 microfarad capacitor. Do we have that? Yes, here it is. 5 microfarad capacitor. Fantastic. Okay. Eighth one. Eighth question. Read this question once. I hope all of you will be able to read this clearly on your screen. Before connecting the circuit shown in the figure, all capacitors are uncharged. The circuit now is in steady state. Okay. Now the switch S is closed. During this time, the steady state is reached again. Match the following. Again, see, now you have to compare what happens to the circuit before and after the switch is closed. Now, before the switch is closed, all the capacitors basically will have some amount of charge on them. Okay, let's call this as Q1, Q2, Q3, and Q4. All of them will have some. The moment you connect this here to the, you switch on this one, then what happens? For the 2 microfarad capacitor, the potential basically should be equal to 10 volts. Earlier, it was not 10 volts because you had minus 10 here, minus 10. So on C2, I should basically have C2, I should have capacitor, the charge increasing. For C2, I'm sure. For C2, the charge Q2 should increase because before it was minus 10 and by minus 10, so it was 0. So there was no voltage. After the switch is closed, C2 will start gaining the charge. I'm very sure about C2. So let me therefore keep an eye on C2 and see which options I can eliminate. In a problem like this, you need to be careful. You should eliminate the answers. That will help you to answer it quickly. Now, what is happening in the first one? Second is the charge on Q2, right? Q2, they give Q, it decreases. No, this should not be the option. One is R, one is basically remains the same. 2 is P. So 2 is P and it increases. Perhaps this can be an answer. Third one, 2 is R. No, wrong. 4 is again, 2 is given to be Q. It decreases, wrong. So I was able to eliminate the answers very quickly and get to answer 2. In fact, 2 is the right answer. You don't have to do everything. You just catch hold of one capacitor, which is easy to analyze, and you can get the answers in no time. So the charge on Q2, C2 will increase, and therefore that's the right option for this. Okay, I hope I made that point clear, how quickly you can answer this question. Ninth question. Yes, ninth question, the figure is missing. I think I need to give you the figure for this. Parallel plate capacitor with square plates is filled with 4 dielectric of constant K1, K2, K3, K4 arranged in this way. Okay, now the arrangement is essentially shown here. I'm going to show the arrangement here. Okay, please look at the arrangement. Arrangement is like this. All right, so there is K1, there is K1, K2, K3, K4, right? So instead of 2, 2, they have given 4 dielectrics here. They have arranged it in this way. Now I have to find out what is the effective capacitance of this. That is the challenge that you have. This is question number 9, isn't it? Yes, 9. I need to obtain this. So let's actually start working on it now. Now these two will be basically in series combination, K1 and K2. So you'll have this to be K1, K2 by K1 plus K2. These two are in series combination. These two again will be in series combination. These two are in series combination. Now, like that, you have these two in parallel combination. So I'm going to therefore write down the effective capacitance of these three. K3, K4 divided by K3 plus K4. And now I need to basically do an addition here because these two are in parallel combination. So the effective capacitance will be given like this. Simplify, you get the answer. Very simple. K1, K2 by, I take the LCM and then work out this to be in this way. Please look at it, take the LCM, simplify it, and see which answer basically matches with this. Which combination, which option basically matches with this. So I think second one is the right option for this. All right. Second one is the right option. So very interesting problem. This figure was missing. Please write down this figure. So these are the two plates of the capacitor being given, and these are the dielectric mediums. So the dielectric mediums are given in this way. Okay, so can I go to my next set of questions? Three capacitors of 4 microfarad are connected in such a way that the effective capacitance is 6 microfarad. This can be done by connecting them. Okay, now let's see what happens in all the 4 options, because all 4 are very interesting. So you want basically you have 3 of them, and you want an effective capacitance only 6. So it can't, all of them can't be in series. If you have all of them in series, then the effective capacitance would be equal to 3 divided by 4. I told you that time. CS will be equal to identical capacitance C by N. So C by 4. So 3 by 4. Sorry, 4 by 3. I'm so sorry. 4 by 3. So the capacitor here will be equal to 4 by 3. So because there are 3 of them of 4 microfarads. So this can be the right option. Many of you are already giving me the option for this B. Okay, let's check. 2 in series and 1 in parallel. So if you connect 2 in series, 4 and 4, that becomes 2. And then I have one more here, 4. So therefore, this will be equivalent to one capacitor here of 2 microfarad, another one, 4. Yes, second one is the right option. All 3 in parallel would have given you C is equal to 12 microfarad. So this also is wrong. 2 in parallel, 2 in series also is wrong. And therefore, this is the answer. 11th, 10th one was quite nice to find out. Okay, let's see what the next problem is telling you about. I'm sorry, I need to rub this off because I have to read this question. A network of 4 capacitors of capacities equal to C1 is equal to C, C2 is equal to 2C, C3 is equal to 3C, C4 is equal to 4C are connected to a battery as shown in the figure. The ratio of the charge on C2 to C4. So I have to find out what is the effective capacitor, the charge on C2 to C4. Okay. Now, finding charge on C4 is the easiest. You know why? Because C4 is connected to a battery here directly in a parallel combination. So the whatever the voltage here, the same will be the voltage here. So the charge on the 4 is the simplest to find out. It should be equal to V into C4, which will be V into 4C. So this will be equal to 4VC. So I have determined what is the charge on the 4 microfarad capacitor. So the only thing that is left here now to find is on this 2C. Now the best way to find out the charge in a connection like this, and look at how the connection is between C3, C2 and C1. They're all in series combination. So C3, C2, C1. And the total voltage here is given to be V. Is given to be V. So the charge on this on the 2 capacitor here, I told you that time itself in a series combination, is CS times V. So find out what is the effective capacitance of this. which will be 1 by Cs is equal to 1 by C plus 1 by 2C plus 1 by 3C. So what will be Cs therefore equal to 6C is the LCM. Am I right? So you get this to be therefore 6C divided by 6 plus 3 plus 2. So therefore Cs will be equal to 6 by 9 plus 2 is 11, okay, into C. And therefore the charge on the 2 microfarad capacitor is 6 by 11 into Vc. 6 by 11 Vc. So you have to find out the ratio of the charge on C2 to C4. So you find out Q2 by Q4, which will turn out to be 6 by 11 into Vc divided by 4 Vc. So Vc will cancel off. You have this to be equal to 6 by 44 is the ratio. 6 by 44 is same as. Did I make any mistake here? Is 3 by 22. Yeah, there is an answer there. No? There's an answer here, which is C2 to C4. C2 to C4. Okay. It should be 3 by 22. The answer given there is wrong. It should be 3 by 22. Okay. Q2 will always be lesser than Q4. I think you can imagine that. No. So the charge on this will be less. So therefore, this should have been written as 3 by 22. Okay. First answer, but should be 3 by 22. So please change the answer for the first option. It should be 3 by 22 is the answer for 11th question. There's a mistake in the option there. All right. 12th one. All capacitors used in the diagram are identical to each other, is of capacitance C. The effective capacitance between point A and B. So let me help you to see this circuit in a better way. Can you all see the circuit now? Can you all see the circuit? So you have the capacitors connected in this particular fashion. Very interesting. And let's see what will be the effective capacitance of this part. See, only consider this part now. This is A itself. If I consider this to be D, this point also will be D. So 1, 2, 3 capacitors are connected across AD. So therefore, this will be written in this way. 3 capacitors like this. Now similarly, this also will be B and this will be D. So there is again another 3 set of capacitors connected in parallel like this. The effective capacitance of this is 3C, this is 3C, and they both are in series combination, isn't it? They both are in series combination. And therefore, what will be the effective capacitance of this? CAB will be equal to 3C by 2. So the answer to this question, therefore, should be 3C by 2. So let us see if that is what we get. Okay. So we'll see if that is what we get. C by 2. So which is 1.5 C. So that should be the right answer for the 12th question. Very simple, very nice, elegant one, I would say. If you're all ready, I will go to my next problem. Can I? Can I go to my next sheet? Okay. 13th question. Since it's a very important chapter, let's not devote any questions. All right. 13th one. A series combination of N1 capacitors, each of capacity C1 is charged to a potential of 3 volts. Another parallel combination of N2 capacitors, each of capacitors is charged to a potential V. The total energy stored in both the combination is the same. The value of C1 in terms of C2 is. That's a nice question. Okay. See, now there are N1 capacitors connected in series. So what is the effective capacitance of this? Would be C1 by N. And it is charged to a potential of 3 volts. So what is the energy of this? will be equal to half CS into 3V the whole square. So therefore U1 will be equal to half C1 by N into 9V square. All right, this is what we get. Now, another parallel combination of N2 capacitors, each of capacity C2 is charged to a potential difference V. Now, in this case, Cp will be equal to N2 times C2, and the energy stored will be equal to half N2C2 into V square, But what is the interesting part? They say that both of them in fact have the same energy. Okay, the total energy stored in both the combination is the same. Okay, is the same. So hence I will have U1 equal to U2, half C1 by N1 9V square should be equal to half N2C2 into V square. V square cancel off, half cancels off, and therefore I can say they are asking you value of C1 in terms of C2. So C1 will be equal to N2C2 by N2C2 N1 by 9. N1 by 9. So just see which one in fact gives you the answer for this. So C2 N1 N2 by 9. So the first one is the right option. That energy the equivalence is what is important here. Okay, 14th one. I think I'll stop with 14th. I will leave out 15th. Okay, for you to do. I'll pass on the solution to it. The resultant capacitance between A and B in the following figure is equal to between A and B. Very nice. 3, 3, and 3. These three are in series combination. So I can replace this with one single capacitor, which will be equal to 1 microfarads. 3 divided by 3. So hence, I will have the combination to be equal to now. Okay, in this way. This is 3. This is 3. This is 3. This is 3. This is 2. 2. And there's one more here, which will be equal to 1 microfarad. 1 and 1 together will be equal to 3, isn't it? Okay. So now the equivalence of this particular circuit will now be 3, 3, one more 3 here, one more 3 here, because 2 plus 1 is 3, and then I'll have one more 3, one more 3, and there's only 1, 2 here left now. So this has become 3. Again, story is repeating itself. 3, 3, 3, all put together in series combination will give you 1 microfarad. Will give you 1 microfarad. So therefore, I can write down that as this entire thing is 1. 1 plus 2 is 3. 3 microfarad. 3 microfarad. 3 microfarad. So across A and B, the effective capacitance is going to be simply 1 microfarad. So CAB will be equal to 1 microfarad. So the answer to this question is the first one. Okay. So let me end my discussion today with this. 15th one, I'll send you the solution, because even I have a class after this. You people will also have a class after this. So see you all then. I just have one more topic to discuss, which I'll do it on Saturday, which will be on current electricity. Okay, again, a very, very important chapter. Lot of questions come on that chapter in the KCET. Okay, with this, let me say goodbye to you all for the day. Have a wonderful
Students, leave the session.
Sir, what do we have at 1 o'clock?
The timetable, it is all sent. Students, leave the session.